Hello, Year 11. Today we're going to start the motion section of forces in motion. The forces section was quite quick, and now we're moving on to motion. So we're going to start off with speed, distance, time graphs. So let's get onto the PowerPoint. Now, let's have a look. So, speed and velocity. Hopefully we remember that speed is a scalar because it is just a number, and velocity is a vector because it is a number and a direction. Now we need to be able to remember this equation. Speed equals distance divided by time. Now you can remember it just as an equation or as a triangle, but this is one that you do need to learn. There's a video there if you'd like to calculate the speed of Usain Bolt from the question. From the video, they'll give you a time, and he runs the 100 meters. You can calculate his speed, but I'm going to go back, and I'm going to we're going to do an example. So a different example than the one that Usain Bolt. Let's just say we've got a person that runs a distance of 200 meters. Okay, and that takes them a time of 40 seconds. What is that person's speed? Well, using this equation, speed equals distance divided by time taken, we can do speed equals the distance, which was 200 meters, divided by the time taken, which is 40 seconds, and that equals, let's see, get my calculator out because my brain has gone completely blank. 200 divided by 45. Okay, that equals 5 meters per second. And we have to remember the unit is meters per second. See, the M stands for meters, the line we can say is per because it's divided by, right? It's the same as a fraction, and S stands for seconds. So, let's move on. Here we have the difference between distance and displacement. So if you look here, this guy's skiing, he's doing the slalom, so he has to go around this one, then he has to go around that one. Yeah, it's like they have to weave in between the flags. Now, his distance he travelled was this red dotted line, so that person travelled 14 meters. Now the displacement is the direct line from where they started to where they finished. Okay, so the distance just has a number, 14 meters. This displacement has a number and a direction, so it should say the displacement was from here, this exact point, to that point, or they could say they moved 8 meters north directly. Now let's have a look at the graphs, because this section is all about reading graphs and being able to understand what they mean. So, what do distance time graphs show us? Well, first of all, what is a distance time graph? Here, a distance time graph is a graph that has distance on the y-axis and time on the x-axis. So just like this graph here. Now, the graph shows us how far away from the starting point this object is at every instant of the journey. So at every time you can see how far away from the start, which was 0, is this thing. So this graph says the person is moving away. So look, it's a straight line. If you look, let's go to a quarter of an hour. they move about 15 meters away. Let's go to half an hour. They've moved 30 meters from the start. Let's go 3/4 of an hour. They've moved 45 meters. So every quarter of an hour they move 15 meters away. So you can see the distance increases steadily as time goes by. So if every quarter of an hour this person moves 15 meters, they will have a steady speed. Let's have a look at this journey. So again, on the bottom it's time, even though it's kind of obstructed, and up the y-axis is distance. So Alice, we're looking at Alice. She starts at 0. Now, it takes her 100 seconds to travel 80 meters. You could actually use that information there to work out the speed of Alice, which we will do later. Now, because this is a straight line, at every point, let's take an instance of 20 seconds. She moves the same distance every 20 seconds. Okay? Now, when she gets to this point here, what you'll notice is the distance is 80 meters. At 120 seconds, the distance is still 80 meters. At 140, it's still 80, and again, and again, and again. So if the distance has not changed, this person is stood still for this length of time. So in a distance time graph, if the graph goes horizontal, the person is stood still. So Alice was stood still for 100 seconds. Then, what you'll notice is this section here is steeper than section A, as in the slope is steeper. In 100 seconds for section A, Alice moved 80 meters. Now, she moves much more than 80 meters. So there's 160 is here. She moves 80 meters in 40 seconds. So actually, in half the time, she moves the same distance. So she's moving faster. And you can see if she goes to 80 seconds, she'll have moved twice the distance that we started with. So she is still moving with a constant speed because it's a straight line, but she is going faster because the line is steeper. Let's do a quick calculation. Now for A here, I'm going to use speed equals distance divided by time. Well, let's have a look. For section A, which is section A finishes here. What distance did she move in section A? Well, she moved 80 meters. She started at 0 and she went to 80, so she moved 80 meters in total. So 80 meters. Now, how long did that take her? Well, she started at 0 and it took her 100 seconds. So let's put that in. The time is 100 seconds. So what is Alice's speed? Well, it is 0.8 meters per second. So this is for section A. Let's have a look at section B. Section B is a bit easier. Well, what is her speed? What distance did she move? Well, she started at 80 meters, and then at the end of this bit here, she finished at 80 meters. So she moved a 0 distance, and that time was 100 seconds. Well, 0 divided by 100 is still 0 meters per second, so she didn't move at all. And if we look at C, well, she started at 80. So this section here, this last section, how far did she move? She started at 80 meters and she moved to 240. So she started there and moved to there. Okay. So let's have a look. Minus 80. I'm getting my calculator in so I don't make a mistake. So she moved, so her speed equals, she moved 160 meters, because from 80 to 240, that is 160 meters. This was in the space from 200 to 280 seconds. So that time she took getting from 200 to 280, that was 80 seconds in total. So 160 divided by 80 equals 2 meters per second. You can see from the graph that they've already worked this out. They did it a different way. Well, actually, it's the same way, but we used the equation speed equals distance divided by time, and we got the same answer for C as they did. They did the gradient. So I don't know how you calculate the gradient in maths, but we remember it in science as rise over run. So how far up the graph did you go divided by how far along did you go. And if you look at what we did exactly that. How far up did the graph go? Well, it went 160 meters up. And how far along did it go? It went 80 meters along. But I'm sure your maths teacher will tell you the gradient is the change in y divided by the change in x. So, how do we describe this journey? Well, we should know it's a constant speed. It took that person 10 seconds to travel 10 meters. We could work out that that is a speed of 1 meter per second. Let's have a look at this next one. Well, we know this is a constant speed up until this point. So this person is traveling at a speed. Then they stop. From this point on, they have stopped. Let's have a look at the next one. Well, this person travels from 0, so they're moving at a constant speed from 0. Remember, the flat line means constant speed. They stop, and then they move quicker for the third section. Because if you look, if I get my pen, okay, you see here, this line here has a slope of this, and this one has a slope of that. If I put them kind of next to each other, do a dotted, you can see the first line is not as steep as the second. So at A they are moving slower, at B they are stopped, and at C they are moving quicker, but still at a constant speed. Well, let's have a look at this one. So I'm going to use, so at A, oh, sorry. Let's get my pen back on. There we are. Right, sorry. So A here, remember this is a constant speed. They are moving forwards at a constant speed. At B, they have stopped. So this is constant forward or positive speed. This is stopped. Now, from this point to this point is C. What do you think they are doing? They started, let's say they started at 4 meters away. 4 meters away, and then they ended up 2 meters away. Well, they've gone backwards. They are moving at a constant speed, but they are moving backwards. Now for D, this line and so A and D look like they are the same slope. So again, they're moving at a constant speed forward, and it is the same speed as A. This one, I won't write on this one because I think you're getting the idea now. They moved forward, they moved backwards, but they went behind where they started. So imagine if you stood at a point, you took 3 steps forward, you then took 6 steps backwards. You would end up behind where you started, wouldn't you? So they went forward, then they went backward, past where they started, kept going backward, then they went forward again, and ended up exactly where they started off. So in this journey, they took 3 steps forward at a constant speed, they took 6 steps backward at a constant speed, then they took another 3 steps forward at a constant speed. This question here is something we need to know. It's quite a difficult one to think about. So it says here, the moon orbits the Earth at a speed of 3,683 kilometers per hour, but has a velocity of 0. How is this possible? Well, have you ever got a ball at the end of a string and just swung it around in a circle? Now, if you stood there for a minute and swung that ball around in a circle without letting go, the ball is still really in the same place. It's just going round and round and round. The ball hasn't really gone anywhere. Because velocity has a speed and a direction, the velocity of this ball at the top is that direction. The velocity of the ball going down is there. The velocity of the ball at the bottom is that way, and going up it's like that. So it goes round and round in a circle. But what happens is, if you're calculating it, the velocity of this side and this side are opposite, aren't they? So they cancel out. The velocity of this side and this side are opposite, so they cancel out. So overall, if you've got something moving in a circle, the velocity is 0. The speed, in this case, is quite large, but because really the moon isn't actually going anywhere, it's just going around in a circle, the velocity is 0. Now we're going to do a task, so you should have taken some notes. Hopefully that was helpful. We're going to do a very quick task. So we're doing the exam question here. If you would like extra speed calculations practice, then open that one and have a go at that one too. But we're going to do this. So let's zoom this in. I'd like you to have a little go at it. So pause the video, have a little go, and then come back while I go through the answers. If you get stuck, feel free to have a look as well. So let's have a look. Part of a bus route is along a high street. The distance time graph shows us how far the bus travelled along the high street and how long it took. Well, we know this is a distance time graph because the graph here, distance is on the y, time is on the x. The bus travels the slowest between points D and E. How can you tell this from the graph? Well, let's have a look. D is there and E is here. What I'm going to do, because I'm going to do this. Try and make it parallel. That's about parallel. Okay. Now, there we go, that's what I want. So if you look here, I line this up to this one, it's about the same slope. If I go next to this one, you see that between C and D the slope is much greater, and between A and B the slope is much greater. Right? Now that term that we are looking for there is gradient. So there are 2 ways you can say this. You can say either the gradient is the smallest, or the slope is the smallest between D and E, Okay, or you can pick a time. So let's say 40 seconds. In 40 seconds, the first one, so let's say A to B, in 40 seconds they travelled 200 meters. In C to D, in 40 seconds they travelled from 200 to 350. So they only travelled 150 meters. So this is for 40 seconds only. Now from D to E, let's take 40 seconds. 1, 2, there we are. They travelled from 350 to 60, 70, 80. D to E, they only travelled 30 meters. So you can see that one is the slowest. So what you'll say is, if you don't want to talk about gradient, is from D to E, in the same amount of time, the bus travelled the shortest distance. Right, between which 2 points was the bus travelling the fastest? Well, that was A to B, because if you look, I already did that here. A to B had the greatest speed because it travelled the furthest distance in the same amount of time. So the bus was travelling the fastest from A to B. There is a bus stop in the high street. This is marked as point B on the graph. What is the distance between point A on the graph and the bus stop? Well, we've done that already actually, because we wrote some stuff down about the graph. A is here at 0. B is the bus stop at 200. So the distance was from 0 to 200. So the distance to the bus stop must be 200 meters. How long did the bus stop at the bus stop? Show clearly how you work out your answer. Well, they've already said that this is the bus stop at B. Now, you can see that between B and C, there is a flat line. It's horizontal. That means they have not moved. Well, they arrived at the bus stop at 40 seconds, and then they started moving again at 60 seconds. So how long were they there for? It was 20 seconds. Well, showing clearly how you do your answer is drawing stuff on the graph, but in this case, you could say 40 to 60 seconds, so they were there for 20 seconds. A cyclist made the same journey along the high street. The cyclist started at the same time as the bus and completed the journey in 200 seconds. The cyclist travelled the whole distance at a constant speed. Draw a line to show the cyclist's journey. Okay. Cyclist. So now we do need our line. Started at the same time as the bus, but completed the journey at 200 seconds. So before I draw anything actually, and I will do it in green. So the cyclist started at the same time, so at this green dot, but it finished at 200 seconds. So this is the finish line right here. It's got to the same point as the bus, but it did it in 200 seconds. So let's go up where 200 is and put our dot there. So now what we have to do is draw a straight line between those two green dots that we just made there. So let's, unfortunately, it didn't quite, it doesn't really want to do it there. We'll do it like that, that'll do. Okay, so I've drawn my green line between 0 and the finish at 200 seconds. After how many seconds did the cyclist overtake the bus? Well, if you look here, so I'll get my red pen out again. The bus at 20 seconds, there's the cyclist. Cyclist is at 50 meters ish, and the bus is at over 100 meters. So if this black line is above the green line, it means the bus is ahead. Well, you can see they cross at this point here. Yeah, they cross at this point here, which is at 160 seconds. It looks like, hold on, let me draw the line down just to make sure I'm not misreading it. Draw it down. It's longer than 160 seconds. Okay. So how many blocks have we got between each thing? 5, 1, 2, 3, 4, 5. So 20 divided by 5 is 4. So each block represents 4. So this is 164 seconds. 164 seconds. That is the point when the cyclist overtakes the bus. So you can tell the cyclist overtaken the bus because the green line is now above the black line. 164 seconds. And that is this done. It's all about reading graphs, understanding what the graph means.